In this lecture, let's discuss the sensitivity analysis. So let's assume the physical plant is described by these dynamic equations. We have A naught, so B naught, lambda naught, and C naught. In real-world scenarios, so the mathematical model we use for controller design is always not the same with the physical plant. But let's assume that A and A naught, so B and B naught, and the C and the C naught, they have the same order. So they are the polynomials of the same order. But the coefficients of A, B, and C differ slightly from those of A naught, B naught, and C naught. Then let's investigate what happens if the system being controlled with the control law, but the control law is designed based on a mathematical model whose coefficients are different from the physical system. So let's assume we use the minimal variance control strategy. Then we know this ut will be the negative qkg over b times fyt. Now let's introduce this controller. So this controller is designed based on a mathematical model. So A, B, and C, and lambda. So you can see from this controller, so we only use the polynomials, so B and F and G. So they are designed based on the mathematical model, not the physical system, not the model of the physical systems. Okay. Now let's find the closed loop transfer function. Like see what will happen if we use this controller to control this physical plant. So let's introduce this controller into the physical plant. So first let's multiply the Q, so negative K on both sides of the equation. So this is gone. Then we know this is ut minus K. So this is ut minus K. Then here, so we have the B0 will be the negative. So the ut minus K will be G over B F times Y. Okay. So if we multiply the BF on both sides of the equation, we have A0 to the BF, then lambda to the BC0F. So then we have the A0, so B plus, so B0, so F, so B0G, so YT will be lambda naught, so B C naught F ET. So based on this identity, this is how we design the minimum variance control. Then this G, so will be the Q K minus 1 C minus A F. So therefore we have the Q K minus 1, so B0 C plus the A0 B minus A B0 times F, and this is the Y, then be lambda, so B C0 F ET. Then we have the closed loop trans function, the closed loop trans function. This would be the lambda naught, so B. So B is from the mathematical model. So C naught is from the physical plan. So F is from the controller design. It's based on the mathematical model, calculation based on the mathematical model. So we have this Z K minus 1. So B naught is from the physical model. So C is from the mathematical model. So A naught from the physical model. So B from the mathematical model. So A from the mathematical model. So B naught from the physical models. And the F is a controller design. So based on the mathematical model. So this is the closed loop trans function. Then to make the system stable, we know, so we must calculate the roots of the characteristic equation. So this is the characteristic equation. So we have to make sure, so all the roots of the characteristic equation, so must be within the unit circle to guarantee the stability. Then if we know the trans function here, okay, so then we know the variance of the output, so can be evaluated using the complex integral. This will be the integration along the unit circle. So this is a trans function of the closed loop system. So we know, so this variance, so under stability of the system, so can be evaluated using the A table and the B table that we discussed earlier. To determine, we use the A table alone, we can determine the stability. If we use both A table and B table, so we can determine the variance. Okay? So once we have the minimum variance control design, then we have to evaluate the sensitivity of the optimum design. Okay, we have to make sure so the design is based on a model different from the physical system. So we must guarantee, so the control design will also work on the physical system. So this is called robustness. But if the optimal system is sensitive to the parameter variations, then the suboptimal strategies can be used to make the closed loop system less sensitive to parameter variations. So this is the identity for the suboptimal control design. So the only difference, we put the B2 here. So here we have the Q N2 plus K minus 1. So this control law will be, if we use the suboptimal strategy, so the control law will be negative. So QK, so G over B1 F. Again, so if we substitute this control law into the dynamical system, so we can find the closed loop system. So let's do it. Okay. So similarly, so let's multiply, so Q negative K on both of the equations. So this is gone. So it'll be Q, so the negative K, then this will be so UT minus K. Okay. So then we know that UT minus K will be the negative, so the G over B1 F by T. Then if we multiply B1F on both of the equations, this will have the A naught, so the B1 F, then have the lambda naught, so B1 C naught F. If we move this to the left-hand side, so we have A naught B1 F plus, we have negative, we move it to the left-hand side, we have plus, so B naught G YT equals to lambda naught, so B1 C naught F BT. So this is the closed loop system. So again, so we have to make sure so the control design works for the control design is based on a mathematical model. We must make sure that it works for the physical system, for the physical plan. Okay, so we have to make sure that the controller will make the closed loop system stable. So we have to make sure this characteristic equation, all its rules must be within the unit circle. So here A naught is from the physical system. So B1 is from the mathematical model. So F is from the controller design based on the mathematical model. So B naught from the physical plans. So G is a part of the controller designed based on the mathematical model. So lambda naught is from the physical plant. B1 is from the mathematical model. The C naught is from the physical plant. So F is part of controller design based on the mathematical model. Then if we know the system is stable, then we can evaluate the variance using the complex integral along the unit circle.